All right, welcome everyone. Today's going to be our 16th lesson of the semester for Calculus 3. So last time we were introduced to the concept of a gradient, if I'm not mistaken, which was a vector that contained each possible partial derivative of a function. So if you had z as f of x, y, it had two components, one for the x derivative, one for the y. And then, oh, is the audio not working? Is it better now? No? Uh-oh. I just moved it a little bit.
To the bank? It's on Indian Town, isn't it? Why not?
Mute.
How far is it?
Okay. All right. Anyways, well, hopefully the audio clears up. Anyways, so we
Not?
figured out what the
It's not?
gradient is.
Lance, mute.
Yeah, please don't unmute yourself. All right. So, anyways, what was I saying? Oh yeah, so we learned about the gradient, right? And we learned it as a method of computing the directional derivative. So if we dotted the gradient with the direction in which we wanted to find our rate of change, we got the directional derivative here. Okay, now let's do a little bit of a review here. So let's say we have this function, f of xy is x squared minus xy plus y squared at this point. All right, so does the directional derivative have maximum and minimum values? And what are those values? Well, first of all, let's just address this question. Does it have a maximum and minimum value? Is that true? Does our rate of change have a max and min? Yeah, that's something we talked about last time. Remember, the value of the gradient, or the absolute value of the magnitude of the gradient, is going to be our maximum rate of change, and then the negative of that will be our max or minimum rate of change, or minimum, excuse me. All right, so let's compute the gradient, and then we can get those values. Okay, let's see the gradient of f. So we have two variables. I'm going to do two different partial derivatives. I do the derivative of x squared and get 2x. I have the derivative of negative xy, and I'm going to get minus y from that. And then the x derivative of this will be 0. All right, and since this function is symmetric with respect to x and y, like if I flipped all the x's for y's and vice versa, it would be the same function. That means I could just do that with the partial derivative. So this will be 2y minus x. And trust me, that's something that will save you a lot of time, especially for more complicated partial derivatives here. But if you're ever unsure of that, of course, you could just take it manually as well. All right, so we have our gradient. Now let's figure out our gradient at the point 1, negative 2. All right, let's see. I plug in 1 here and get 2. I plug in negative 2 here, and then I get 4. All right, I plug negative 2 into here, get negative 4, and then minus 1 will be negative 5. Okay, so this is going to be my gradient at the point 1, negative 2. And the magnitude of my gradient at that point is the square root of 4 squared plus negative 5 squared, aka the square root of 41. So this is going to be my maximum rate of change. And then what is the minimum rate of change going to be? Not 0, minimum as in like lowest valued number. Yeah, negative square root of 41, that's right. There we go. So if we can go up the hill that's this steep, we can also go down that very same hill that's also this steep. Okay, now let's ask ourselves this question. This is a little different from what we done last time. In what direction is there no change in the function values? Well, let's kind of think of a physical example here. So let's say my hand here is like a slope, right? And this is the direction of steepest descent, and this is the direction of steepest descent. So if I'm right here, then which way would I go to have no change in my height at all? And it looks like people are already saying some answers here. We're going to go perpendicular. We're going to go left and right rather than up or down right here. So we're going to go in a direction that's perpendicular to the gradient. Okay. What's a vector that's perpendicular to 4, -5? Does anyone know what's going on here? What's perpendicular to that? I guess 0, 0. Yeah, technically, I guess, but something a little more non-trivial would be 5, 4. So this is going to be the direction in which there's going to be no change whatsoever. Now, how did I just divine that answer? Where did I get that from? Well, if you ever have a vector AB and you wish to dot it with something that will give a result of 0, you could always do -BA, like that. Or we could do B, -A. Both of these are going to be 0. And the reason is because we get one of these products being -AB and then the other one being +AB. So what I did was I just flipped the numbers and I changed one of the signs. So this is going to be the direction. And I guess we could also include this as well. These will be the two directions in which there's no change in the function values, i.e. we're going to be perpendicular to the gradient right here. All right. So let's take a visual look at what's going on with this. And we did this algebraically. Let's see a visual here. So let's say we have this surface, right? And here's the point where we are on the surface. So if we want the maximum amount of change, that'd be going up the slope this way. Or if we want the minimum or lowest or most negative value, that'd be going down this way. Now, if we want to just stay at the same value, rather than going up or down, we're simply going to move to the left or the right here. And if you look at the shadow of this down here, the projection on the input values, these are going to be right angles. So those directions are going to be orthogonal to each other here. All right. So let's see here. Yeah, so to summarize everything, the function does not change at AB in any direction orthogonal to the gradient. Also, let's remind ourselves about this concept here. So if we have a function of x and y, and that's equal to some particular k value, where k is something that we can kind of just change at our, oh, is there, can I unplug the mic and plug it back in? Okay, is that better? Is that better? All right, perfect. Yes, the ultimate technology solution there. Awesome. All right, anyways, so let's remind ourselves what a level curve is. It's where we have some combination of x's and y's equaling k, where these k's, you can imagine them as different z values. Let me just write that out. Okay. So when we go along a particular z value, when we're fixed at the z value, we would kind of follow along a curve, something like this. Like for example, for this, for this function up here, a level curve would simply be these concentric circles, because as we go lower and lower z values, our circles are getting tighter and tighter as we go down. So this would be a level curve. Now notice something about the level curve. The level curve is going perpendicular to the gradient here. So the gradient is having a maximum increase or maximum decrease, whereas the level curve is just staying at the same value. So that gives rise to this result right here. If we have a differentiable function, meaning we can find our gradient reliably, then the line tangent to the level curve at AB is going to be perpendicular to the gradient there. So if we kind of take our tangent line to this right here, oh, picture's just a little bit too high. If I take my tangent line here, we see the gradient will be perpendicular to that as well. All right. So let's see here. Let's go back to that same example that we were looking at earlier. All right, so consider the function f of xy is x squared minus xy plus y squared. And we're all, again, looking at that point. So what we're going to do is we're going to find a tangent vector to this level curve at the point 1, -2. All right, well, let's see here. Oh, let's actually see it. Let's not have it be so far down. So here is the tangent that we want, right? Here's our level curve. This is an ellipse that happens when our z value is going to be 7 right here. And then we want to figure out a vector that's going to be along this tangent line here. Well, what vector is that going to be? Well, we remember that the gradient vector for this was, actually, I don't remember what it was. Let's see what it was. It was 4, -5, right? So here's the gradient, and then we just want something perpendicular to that. That will move along the level curve. So the vector that we want here could be 5, 4, which is the vector that we found last time, and it's the vector in which our function is not changing value if we move in that direction. Okay, so pretty much the moral of all of this is that if you follow the gradient, you're going to have either steepest ascent or descent. And if you go perpendicular to the gradient, you're going to have no change in the function value at all. That's kind of the summary of the past 3 pages right here. All right. Now, what we're going to do is we're going to return. So that was a tangent line, right? We found a vector in the direction of this, this tangent line here. So what we're going to do is we're going to kind of expand this notion of all the stuff we just talked about to tangent planes. Okay, now let's see here. A surface in R3 may be defined in at least 2 different ways. So the usual way that we're used to it being defined is z is a function of x and y, like the ones we just looked at. Like we may have z equals, or maybe f of x, y is a formula with x's and y's here. To the left, there's nothing written to the right here. Well, I guess there's this part up here. Okay, so this is the form that we like, and this we already know how to find tangent planes to functions like this. I think we talked about it in lesson 13, if I'm not mistaken, right, when we learned about partial derivatives. Now, unfortunately, life's not always kind enough to be give us formulas in this form right here. So what may happen is that the z may be mixed up in the formula in some way. Like, for example, we have z squared plus x squared plus y squared is 4. This is an example of something given implicitly. Or yes, so you could either have it be equal to 0, or you could have it equal some kind of constant. So you may see it written this way, or you may see it written where everything is on the same side. It's going to work the same way in either case. But the main point is that z is mixed up into our formula right here. All right. So now we already dealt with tangent planes, just like I said. Here's the equation of the tangent plane if we have z as a function of x and y. We have z minus f of ab is our partial derivative times x minus a, and our y partial derivative times y minus b right here. But we didn't talk about getting tangent planes if the z is maybe mixed up into everything here. So we're going to talk a little bit about that, and our friend the gradient is going to help us, help enable us to do that. So this is what I'm about to say is the main crux of everything I'm getting at here. I feel like I'm kind of saying the same thing over and over and over again in slightly different ways. Here's what's going on. So remember that the gradient was perpendicular to the level curve at that point, meaning you could either follow the gradient to have the most extreme change in your function, whether up or down, or you could follow along the level curve and have absolutely no change in your function. So in the same way, if we move all of our variables to one side and end up getting a function of 3 of them, then the gradient of that will be perpendicular to the level surface, where we set all of this equal to some constant value at the point A, B, C. So what this is saying is that if we move all of our variables to one side and we look at the gradient, then this will be perpendicular to the level surface right here. All right. So this actually allows us to get our this allows us to get the equation of a tangent plane to something that's not just z is f of x, y. And the way that's going to happen is we're going to use the fact that we just stated. So we're going to, well, we don't need a vector symbol. We have f at the point a, b, c, and then we're going to dot it with x minus a, y minus b, and c minus z. And this dot product is going to end up equaling 0 because these guys were going to be perpendicular here. Now, if we actually carry through with the dot product here, then we end up with this. Partial f partial x with x minus a. And then, oh, I guess I should call this capital F. Whoops. This is going to be capital F here. So we have partial capital F, partial x, and an x minus a. Partial capital F, partial y, with y minus b. And then flip the third one. Oh, thank you. Z minus c. And then partial f, partial z, z minus c, 0. So this is going to be our new tangent plane. Now, this part is the part that's different. You may recognize these from the original form for our tangent plane here. Oh yeah, why is it big F and not lower f? Well, big F, we're denoting big F when we have the z mixed in with the rest of the formula. And we traditionally use little f if we have z on one side and then the x's and y's on the other. So big F usually means that z's mixed in there in some way. And we might not even be able to solve for z, actually. Here we might be able to kind of say a plus or minus something, but in many cases we can't solve for z at all. But even in those cases where we can't, we could still end up finding a tangent plane by following this formula here. So we have our big F with all the x, y's, and z's mixed together. And then we have these two terms which we had previously, but now we have this new term right here to account for the z's being mixed into our formula right here. All right, so for a surface, it can be equivalently written f of x, y, z is f of x, y minus z equals 0. The tangent plane to the surface at this point is going to be, well, we have, what this part is saying is that this is the general case of the tangent plane formula that we had earlier. So in the previous lesson, we ended up having this guy, right? This was our tangent plane here. And then now I'm saying that we can have this equation as well. And it turns out that the old one is a special case of the new one. Because if we have z is written as a function of x and y, then I could subtract z over and get 0. And this is technically going to be my big F, right? This is going to be a big F because we mixed the z in with the x's and y's right here. So now if I do partial f partial x, well, let's see. If I do partial f partial x of this, I just have the x derivative of that. And then I have my x minus a. But there's no x derivative of a z if it's taken to be an independent variable like these. So partial, this is going to have a 0 x derivative. Same thing happens with the y. I do the y derivative of this stuff right here. I get this. And then I do the z derivative of this stuff. Let me ask you guys this. What's the z derivative of this going to be? -1, that's right. So we have -1, z minus c is 0. And then if you add this over, then we end up getting the old formula for the tangent plane. So remember, these guys are pretty much the same here. This right here, and then this right here. Are these lower or uppercase f's? They're lowercase. I put the little hook on them. But yeah, as you can see, we have the same equation here that we do here, where c is going to be f of ab right here. So we can get the old equation from the new one. So now in general, how would we practically use this? What I would recommend doing is I would use this formula, the old tangent line formula, if you already have z as a function of x and y. But if your z is mixed up with the other variables, like maybe you have something like this, then I would use this new formula to end up getting your tangent plane here. We didn't subtract f of a, b in the old formula, right? Well, yeah, it's right here. Yeah, so we have that. And then the c here, this is going to be f of a, b, because when we plug in a and b into our f, which is z, we end up getting this c right here. And this is a tangent plane. All this stuff is about tangent planes. Okay. Now, one thing that we're going to have to compute sometimes is what's called a normal line. Okay, so what's a normal line? The line through the point P on a surface having the direction gradient of f is called the normal line to the surface of P. So what is all of this looking for right here? Or what is this talking about? So let's say we have our surface. Maybe it's kind of like a bent thing like this right here. And then here we have our tangent plane at this point. So what would the normal vector of this tangent plane be? Well, it would look something like this. But remember, this is going perpendicular to our surface, right? So what's another name for this? So this is our normal vector, but it's also the gradient at this point. So when we're going to find the normal line, the gradient is the direction, or as I like to call it, the slope vector. And the normal line would be if we just extended this down like that, and then up like this. We can imagine this kind of piercing through the surface, and it's going in the same direction as the tangent plane right here. So that's what the normal line is. So all we have to do is just figure out what the gradient is, and then put in our point, and then we'll be good to go in getting this normal line here. Okay, we've had a lot of theory. I don't think we've done a problem in a decent bit here. So let's do something and kind of try to bring ourselves back down to earth here. So find equations of the tangent plane and the normal line for this surface at the point 1, 2, 4. And for practice, I could easily make this z equals 9 minus x squared minus y squared. But I'm going to practice using my new formula for the tangent plane, so we can get some practice with that. All right. So what's our new formula for the tangent plane? Well, this is called f of x, y, z, but it's if we're consistent with our old notation, it really should be capital F, because we have everything on one side and then 0. So I'm going to call it capital F to be more consistent. So the tangent plane equation here is going to be this, where we have all of our different partial derivatives, and all of them are going to end up equaling 0 when multiplied by x, y, and z minus the point. All right. So let's see here. All we need to do is just compute some partial derivatives then. So we have partial f, partial x. Let's see. The only x's I see in here are this. So it's going to be 2x. And it looks like the situation is the same for the y's. So we have 2y. And then finally, partial f, partial z. That also only appears in one place right here. It's just going to be 1. All right. Now we want to do this at the point 1, 2, 4. So we're doing this at 1, 2, 4 specifically. So our partial f, partial x, well, let's see. It'll be 2 times 1 will be 2. Partial f, partial y. We have 2 times 2 will be 4. And then partial f, partial z, well, that's going to be 1 no matter what, because that's a constant. All right, so now we're ready to fill in everything for our tangent plane. So we put the 2, this coefficient, next to the x minus a. So we have 2x, and then our a value is 1. That's our specific x value that we have here. We have 4 times y minus b. Let's see, our b is 2 for this. And then we finally have 1, and then we have z minus 4. And then all of this is going to end up equaling 0 right here. Is it possible to have tangent surfaces for a function and then we do this with a w? Yes. You can up this kind of reasoning any number of dimensions that you like, although it gets it gets harder and harder to visualize the more dimensions you move up. So yes, you could have a tangent 3D space. But we're not going to cover that explicitly. But yes, all of this reasoning does apply to higher dimensions as well. All right, so here is our tangent plane. If we want, we could solve for z here, maybe multiply this out. 4y minus 8 plus z minus 4 is 0. So let's see here. I have -10, -14. I'm going to add that over. Minus 2x minus 4y. All right, so there is our tangent plane right here. All right, now that wasn't the only thing we wanted to find. We also wanted to find the normal line for this tangent plane. But all we need to do to find the normal line is to take our gradient at the point, which we actually already know. It's going to be 2, 4, 1. And we make this the direction vector for our line. So this is going to be our direction or slope vector right here. Okay, so that means that some parametric equations for our lines would be x. Now this is going to be our direction vector or slope. And then the point we want to go through, which is the same point we used up here, is 1. Then we have y is 4t plus 2. And in the same way, z will be t plus 4. And there we go. So we have parametric equations for our normal line. Is there a case where this needs to be a unit vector? Right here, this does not need to be a unit vector. Remember, the direction vector doesn't need to have magnitude 1 in order for this to be a slope. Can we also get it from the plane equation? Yeah, you can get it from here because we're essentially just reading off these as our slopes and then these numbers that are being subtracted as our points. So yeah, you could read it off of that if you want to as well. All right. We have technically done this for exam 1 material to find normal lines. I guess you would need to know what a tangent plane is. But if you knew what a tangent plane is back then, you could use your normal vector as the direction vector for a normal line. So almost. Will things be explicitly stated between little f and big F? Yeah. In the purposes of today's lecture, big F means that the z is mixed in. Little f means that z equals that, and then we have just x's and y's. That's what big F and little f mean today, but everything else will be explicitly stated in the future. Yeah, this is probably a mistake there. Okay, so let's do something else. Let's find equations of the tangent plane and the normal line to this surface at the point 1, 2, 1. So we're doing the same thing, just with a different surface right here. Now in this one, I guess you can maybe solve this for z, but it's a little bit more mixed in than the previous one is. So let's try using our new formula for the tangent line. So we have partial f, partial x, x minus a, and then the same for all of the other derivatives. Or sorry, all the other variables. All that's going to be 0. All right, so let's go ahead and take our partial derivatives here. So let's see. F sub x. I'm going to get y here. I'm going to get 0 for this because there aren't any x's. And then I'm going to get tangent plane. Thank you. Tangent plane, absolutely. So we do the x derivative here and get y. We do the x derivative here and get 0. And then we do the x derivative here and get z. Okay, so we end up getting the x derivative is y plus c. Let's take a look at the y derivative. Let's see. So we have x plus z and then nothing. Okay, and we actually can see that this function is symmetric with respect to x, y, and z. So you can interchange any two of them and it'll still be the same function. So that immediately means we know what fz is. What's fz going to be? X plus y. That's right. Okay. So these are our three partial derivatives right here. Okay, now we're doing this specifically at the point 1, 2, 1. So f sub x is going to be 3. F sub y is going to be 1 and 1 is 2, I think. And then fz is going to be 1 plus 2, which will be 3 right here. Okay, so we know all our partial derivatives, and then we also know a, b, and c because those are the specific values that we have here. Yeah, thanks for the confirmation reading. All right. So we have 3 x minus 1, 2 y minus 2, and then 3 z minus 1 gives us 0. All right. So there we go. So there's our tangent plane. And if we want, we could solve this once again for z and get what that is. All right, now we want to find the normal line. But as you guys observed, the normal line, you can effectively read off the same information that we had for the tangent plane right here. So the x component of our normal line is going to be the partial derivative here. And then we multiply that by t, and then we add the specific a value, which is 1. Y is going to be 2t plus 2. And finally, z will be 3t plus 1. So here is our normal line right here, made up of the point P, and then as the direction vector, it's going to have as the gradient at that particular point right here. So that's what the normal line is. Okay, the next one's a little bit more involved. So let's see what that is. Okay. The surfaces x squared plus y squared minus 2 is 0, and x plus z minus 4 is 0, meet in the shape of an ellipse E. And they were kind enough to provide us with a picture right here. So this you may recognize as a cylinder of radius √2, if we move this 2 over. So here's our cylinder. And then this is a plane. So this is some diagonal plane here. And where they meet is going to be an ellipse. It's going to look like this right here. All right. So what do we need to do? Find parametric equations for the line tangent to E, the ellipse, at the point 1, 1, 3. Okay, so here's the point 1, 1, 3 right here. Now, let's see here. Here is the normal vector of the plane, which is also going to be the gradient of this. Remember, the gradient of a surface is effectively going to be the normal vector to that surface. And in the same way, even though this isn't a plane, we can imagine that the gradient of this is the normal vector to this surface, which points this way. Now, if we take the cross product of these, if we do our cross product, we end up going along the tangent line to the thing that's at the intersection of both of them. So if we cross F and G right here, then we end up getting our tangent vector right here. And then from that, we can make our parametric equations. So what do we need to do? We need to figure out the F gradient. We need to figure out the G gradient. We need to cross them to get this, and then we'll have the direction vector for our line right here. All right, so let's go ahead and do it. So what's the gradient of F? Let's see, we have 2x for the x derivative. We have 2y here. And then there aren't any z's at all. So that's going to be 0. All right, and then now if we look at the gradient of g, this one will be even easier, in fact. The x derivative of this will be 1. The y derivative of this will be 0. And the z derivative will be the constant 1. All right. Let's see, why doesn't our handy-dandy formula work on this? Because we're not looking at just one surface here. We're looking at the intersection of two different surfaces. So it's going to be a little bit of a a different kind of situation here. So that's why we can't just do it the same way that we did it for the previous problems here. Why are we crossing them? Because the vector that's perpendicular to both of these will be the tangent vector to our ellipse right here. We want it to be perpendicular to both of them, so it follows along the ellipse right here. All right, and can we do this for any intersection? Yeah, absolutely. So if you have the intersection of two surfaces like this and you want to find something parallel to the tangent line here, then yes, you can absolutely do the same thing for any other situation. All right, so let's get our gradients at the particular point. So this is at the point 1, 1, 3. Well, this is a constant vector, so we know what that's going to be, 1, 0, 1. And then when I plug these into here, we have 2, 2, 0. All right, so now I'm going to cross these here. And we can cross gradients together because they're both vectors. We have I, J, and K. We have 2, 2, 0, and 1, 0, 1. All right, so we need to dust off the old cross product skills and see what this is going to be. So for our I component right here, we have 2 times 1 minus 0 times 0 is 2. Then for J, we have 2 times 1 minus 0 times 1, so we get 2, but our friend J likes to be negative, so we put a negative there. And then finally, we have K, which would be 2 times 0 minus 2 times 1 will be negative 2. Now remember, this cross product is going to be, our direction vector right here. Oh, does F always come first in the cross product? No, we could have done the cross product the other way. We could have done G cross F. We just would have gotten the vector going this way instead. But that would have been perfectly valid for getting our what we wanted here. All right, so now we have our direction vector. Let's write down the parametric equations that they wanted. So we're going to have x is going to be 2t, and then the specific value we're at is 1. And then we have y is going to be negative 2t plus 1. And then finally, z will be negative 2t plus 3 right here. So there we go. So this is going to be our tangent line at the intersection of these right here. All right. Let's see. How are we doing on time? Are we doing all right? Oh, yeah, we're doing pretty well, actually. All right. So we have one more problem that we're going to do here. Can you write the vector as 1, negative 1, negative 1? That's right. Yeah. Remember, for lines, it's the relative sizes between each of these that matters. So we could have taken anything parallel to this vector, which includes 1, negative 1, negative 1. And yeah, that would have also worked as well. All right. So let's see here. Now what we're going to do is we're going to find the angle between two surfaces. So on the one hand, we have this sphere, x squared plus y squared plus z squared is 9. So it's a sphere of radius 3. And then we have x plus y plus z squared is going to be 1 right here. I don't think this one has a nice name or anything. Does it? I don't think so. But yeah, we're just going to look at the angle between these. Now, what does that actually mean? We're just going to look at the normal vectors that they have at that particular point, and we're going to see what the angle is between those. And that will emulate what the angle between the two surfaces is going to be. Okay, well, that means we need normal vectors, aka gradients, to each one of these. So I'm going to call this one, I'm going to call this F right here. And then I'm going to call this one G. Give some names to these right here. All right. So let's take a look at the gradient of F. Let's see. Actually, I think the gradient of all the components of the gradient will be pretty similar. we're just going to get 2x plus, or not plus, 2x, 2y, and 2z right here. Meanwhile, the gradient of g here, let's see, we have the derivative of x is 1. We have the derivative of y is 1. And then we have the derivative of this will be 2z. Now we're doing this, we're trying to find the angle at the point 2, -2, 1 right here. Okay, so what do these gradients become at that point? So, oh, is the audio being bad again? Okay, let me try the magic trick here. Let's see if this works again. Okay, how about that?
That's
Okay?
great. Yep.
Good. All right, wonderful. All right, let's get back to it then. So this gradient here for f is going to be 4, -4, 2. Meanwhile, the gradient of g will be 1, 1, 2. Okay, here. Now we want to know the angle between these two vectors right here. Can we make that gradient 2, -2, 1? That would be the gradient anymore, but it would actually give you the same answer in this problem here. Because what we're going to do is we're going to take the dot product of these two. And why on earth would we do that? What's the point of doing the dot product of these? Well, remember what the dot product is. It's the magnitude of the first vector times the magnitude of the second vector times cosine of the angle between them. And this is what we want right here. We want the angle between them. So what we're going to do is we're going to divide by these magnitudes. So what you were thinking of, it's not the gradient of 6, it's the gradient of g. There we go. So what you were saying, if we were to divide this by 2, that would technically work, but it wouldn't be the gradient anymore. But it would give you the same answer because we're dividing by the magnitude of it. All right, anyways, let's go ahead and compute what this is so we can get cosine of our angle here. So what's the dot product between all of these? So we have 4 times 1 is 4. We have -4 times 1 is -4. And we have 2 times 2 is, well, 4. All right, now let's take a look at the magnitude of f here. So that's a square root of 4 squared plus 4 squared plus 2 squared. Actually, I'm going to write this as 4 just to keep the theme going. This is a 4 now. And then we have, oh, this is going to break it. We have the square root of, or the magnitude of g, which is the square root of 1 squared plus 1 squared plus 4. Almost had all these 4s right here. All right. So let's see. These will cancel out and give us 4. 16 plus 16 plus 4 is going to be 36. So this will be a 6 down here. And then we have the square root of 6 right here. And we could simplify this to be 2 and then over 3 root 6. Okay, now what is that? That's not quite an angle. Cosine of the angle is equal to this. So that means that the angle itself will be cosine inverse or arc cosine of 2 over 3 root 6. And looking at this number, I think this number is relatively small. So these angles are going to, these surfaces are going to be almost perpendicular to this right here. Oh, turn the 1s into 4 over 4? Yeah, I guess I could have done that. All right, there we go. So that's how we find the angle between two different surfaces. So let me try to draw a picture of this. Might not be very good. Let's say we have these two surfaces right here, and they're intersecting. That's terrible. Right. Okay. So they're intersecting right here. So we have the normal vector for one of them pointing like this, and we have the normal vector for the other one pointing like that. So what we want to do is we want to see the angle that we go between them here. Art Major Manley, yeah, there's no one. Yeah, sorry. Yeah, but you pretty much just take the two normal vectors to your surfaces and then see which way they're oriented. And then that's how we get this angle. All right, that looks to be about it for today. So this is all we're going to talk about in terms of computing derivatives and tangent planes. Now we're going to put some of this into practice. So next time we're going to apply derivatives to find mins and maxes, which is very much the same thing that we did once we learned derivatives in Calc 1. So we'll see what the Calc 3 version of this is going to be next time. All right, so that's it for the recording. Sorry, I've been really distracted today. I kept losing my train of thought.